Greetings. My name is Elizabeth Wade. I teach basic calculus for the mathematics department at Pellissippi State Technical Community College. This is topic 5 on integration and segment 5.5 on definite integrals. In geometry, we learn to find the area of rectangles, triangles, circles, etc. But what if we wanted to find the area of this shaded region shown in this diagram? This region is unusual because it's bounded on the top by the function x squared plus 1. It's bounded on the bottom by the x-axis, on the left side by the vertical line x equals 0, and on the right side by the vertical line x equals 4. We could approximate the area of this region by subdividing it into 4 rectangles and using the sum of the areas of these rectangles to approximate the area of this region. There would, however, be some error involved. You can see that these rectangles, for example, right here, this falls short of the actual area, so this would be some error in here and here and here. This would be 0, 1, 2, 3, and 4. And what I've done is I've drawn the 4 rectangles, and I've built these rectangles on the left side of each subinterval. What I'm talking about, let's look at the subinterval that runs from 2 to 3. I went to the left side of this subinterval, took the number 2 to determine the height of this rectangle by plugging 2 into the function. F of 2 is 2 squared, which is 4 plus 1. So the height of this particular rectangle is 5. And the width of this rectangle, when we go from 2 to 3, of course, is 1 unit. So f of 2 times 1 would give me the area of that particular rectangle. And then you would do the same thing for each of the 4 rectangles. And in doing so, you come up with an estimate of the area of this region shown in the first diagram to be 18. But we realize that this is an underestimate because of this error that we discussed a minute ago. Notice that if we increase the number of rectangles, then the amount of error decreases, so the approximation improves. You can see that the error involved here is smaller than it was before, and it becomes even less here as we continue increasing the number of rectangles. This is with 8 rectangles, and this is with 16 rectangles. So in general, we can state that as the number of rectangles, n, approaches infinity, the sum of the area of these rectangles actually approaches the actual area of the region. And we come up with the theory that, in general, if f of x is a non-negative continuous function on a closed interval from a to b, then the area under the graph can be represented by this expression. Let's look closer at what this expression involves. First of all, I have f of x sub 1 times delta x plus f of x sub 2 times delta x, etc. Well, the x sub 1, the x sub 2, the x sub n would be points inside each of these rectangles, that is, points on each subinterval. And when we plug them into the function f of x sub 1, f of x sub 2, etc., we are actually determining the height of the rectangles. And then delta x is the width of each rectangle. So we do this for each of our n rectangles, and then notice out front I wrote the limit as n approaches infinity. We let the number of rectangles approach infinity. And in doing so, then this becomes the actual area of this shaded region. We denote this shaded area by this symbol, the integration sign with an a at the bottom, which is called the lower limit, and a b at the top, which is called an upper limit. The integral from a to b of f of x dx. And this represents the area under this graph from a to b. And again, this can be written as the limit as the number of rectangles approaches infinity for the sum of the areas of each of the rectangles, f of x sub I and delta x sub I. And this expression, f of x sub I delta x sub I, again, is the area of each rectangle. We have n rectangles. We sum, this is a summation sign from mathematics. We sum the areas of these rectangles and let the number of rectangles approach infinity. And once again, this expression is called a definite integral. So let's write a definite integral to represent the area under the function x cubed minus 2x squared plus 6 on the interval from -1 to 2. Well, I have graphed x cubed minus 2x squared plus 6, and you can see the graph here. We want to get the area on the interval, the closed interval from -1 to 2, so I'll locate -1, drop a vertical line, locate 2, draw a vertical line, and this is the area that would be bounded, the area under this function from -1 to 2. And the definite integral that would represent this area would be the integral from -1 to 2 of the function x cubed minus 2x squared plus 6 dx. Well, that is it for this segment. Now you need to practice this concept by working similar problems. Good luck.